Hello everyone. So this is the second lecture of power electronics. So here we will understand what is classification of semiconductor switches. So we can classify that semiconductor switches in three categories. So classification by control, then classification by charge carrier, classification by power handling capability and switching frequencies. Okay, let's move to that classification by control. So before going to that classification by control, we'll understand what is ideal switch and what is practical switch. So in a simple comparison, we can say that ideal switch is a lossless switch and practical switch means losses will be there. So here I have shown that four graph. So 1, 2, 3 and 4. These four graph will represent the different characteristics of ideal switch and practical switch. Graph 1 and 2 represent the characteristics of ideal switch. Here we can see in the graph 1 we can see that current is there is some current is there but voltage is 0. So we can say, so in case of that off state of a ideal switch voltage is 0, that current can be minus infinity I infinity. So this is the condition. So for that off state of a ideal switch, so that's why what will happen now. So because of that, P of is equal to 0 as voltage is 0. Now if we see the characteristics of on state, so here that current is 0 but voltage has some value. So what we can write, that current is 0, that voltage will be minus infinity to infinity. So this is the condition. So here also P on is equal to 0 as current is 0. So from the ideal switch you can say that power loss is 0 in case of a off state and on state. Now if we see the practical switch, that graph 3 and 4. So if we compare that graph 3 and 4 with the graph 1 and 2, so here some values, it is showing some values. This represents some values, means here in case of that off state of a practical switch, V not equal to 0, and here in the on state current not equal to 0. So that's why this P off also not equal to 0 and P on is also not equal to 0. So that's why there will be some delay in the switching. So this is the basic comparison of a ideal switch and practical switch. So in case of that practical switch, by applying some control signal, by applying appropriate control signal, we can turn on and turn off that switches. So now we'll see that classification by control. So if we classify these switches based on their control, these semiconductor switches is classified into three categories. One is uncontrolled, semi-controlled and fully controlled. So in case of a uncontrolled switch, the example of uncontrolled switch is a diode, PN junction Schottky diode, first recovery diode and TRIAC. And semi-controlled switches are that SCR and TRIAC, and fully controlled are transistor, MOSFET, MCT, IGBT, GTO. So why it is called uncontrolled? Because nothing. So there is, in case of that switch, there is a two state. One is on state, another one is the off state. So if we can control on and off both, so then it is called fully controlled. Where it is both are controlled, that on and off is controlled, so that's why it is called fully controlled. Now in case of a semiconductor switch, either on or either off we can control, so that's why it is called semi-controlled. Now here nothing can be controlled, not on and off, nothing can be controlled, so that's why it is called uncontrolled switch. Okay, let's see why these switches are uncontrolled and these are semi-controlled and these are fully controlled. So uncontrolled switch, like PN junction diode is a uncontrolled switch. If we see the symbol of a PN junction diode, so that is like this. So there is anode, cathode. This is a two-terminal device. This is a two-terminal device. So there is no third terminal like gate or base. So there is no third terminal. So that's why it cannot be controlled. So when it is in forward bias, so that is switch on and off based on that their applied voltage. When there is a forward bias, then it will be on. When it is reverse bias, it will be off. So we cannot control externally, independently. So that's why this is called uncontrolled switch. Now in case of that Schottky diode, so there in Schottky diode, if we draw the clear diagram, so there is one metal region, another one is the n type. So here also only two terminal, so that's why anode and cathode. So that's why it is not possible to control by using that third terminal. So that's why this Schottky diode is also called a uncontrolled switch. Now if we talk about that first recovery diode, so that is similar as these two devices, PN junction diode and Schottky diode. So in these also there is no third terminal, no gate or base, so we cannot control at all these three devices, that fast recovery diode also. So that's why this is also a uncontrolled device. Now if we talk about the TRIAC, so let's see the symbol of a TRIAC, that is like this. So here also only anode and anode 2, there is a anode 1. So this here also there is two terminals, so this is also a two terminal, so there is no gate or base to control the turn on and turn off. So that's why this is also a uncontrolled switch. So that's why this PN junction diode, Schottky diode, fast recovery diode and TRIAC is, all these devices are called a uncontrolled switch. Now let's move to the semi-controlled switch. So some example of semi-controlled switch are SCR and TRIAC. So let's see the SCR and TRIAC. Let's see the layer diagram of a SCR. So this is look like this. So this is a 4-layer device, 2, 3, 4, that is P, N, P, N, that anode, cathode and gate. So when we are applying that positive voltage across the anode and negative voltage across the cathode, and again another supply is connected, that positive to the gate and negative to the cathode, so in that case thyristor will be on. So means by using this gate terminal, so if we see the symbol is look like this. So that is anode, cathode and gate. So by using this gate terminal we can turn on this SCR. So that's why but so it is not possible to turn off by removing this gate pulse. So by removing this gate pulse it is not possible to turn off this SCR. So that's why SCR is called a semi-controlled device, semi-controlled switch. Okay, now move to the TRIAC. So first draw the symbol. It is look like similar as TRIAC, only difference is that there is a third terminal. So this is look like TRIAC, but there is one third terminal, so that is gate. So here gate is there, MT2, MT1. So this is the symbol of a TRIAC. So here also like turn on is control, so meaning it can be turned on by applying a gate pulse. So by applying this gate pulse it can be turned on, but turn off is uncontrolled, means once conducting it cannot turn off by gate control. So that's why this is also called a semi-controlled device. This is semi-controlled switch. Okay, these two switches are semi-controlled switch. Now we'll see that fully controlled switch. So that fully controlled switches are BJT, MOSFET, IGBT, GTO and MCT, means on and off both can be controlled for these 5 switches. BJT has two types, NPN and PNP type. So here there is a one collector, base and emitter junction. In case of that PNP also emitter, collector and base junction is there. So here by using this base current, it can be controlled, means once current is applied it will turn on, by removing the base drive it will be turned off. So that's why this BJT is called fully controlled device. MOSFET. So MOSFET also two types, one is N channel and another one is the P channel MOSFET. So this is the symbol of N channel MOSFET. So the three terminal is drain, source and gate. Drain, source and gate. So this is the symbol of N channel MOSFET and drain, source and gate. So this is the symbol of P channel MOSFET. So here also the turn on and turn off can be controlled by voltage at gate terminal. So means by applying that voltage it can be turned on, and by removing the gate voltage it can be turned off. So that's why MOSFET is also called a fully controlled device or fully controlled switch. This IGBT is the combination of MOSFET plus BJT. So this symbol is like this. So it has also 3 terminals, so that is collector, emitter and gate. So here that it is controlled by gate voltage like MOSFET. It is controlled by gate voltage like MOSFET. So when we apply the gate voltage, it will be turned on. By removing the gate voltage, we can turn off this IGBT. So that's why IGBT is also called a fully controlled switch. Now see that GTO. GTO is that gate turn off thyristor. Gate turn off thyristor. Gate turn off thyristor. And symbol is like symbol is like this. Symbol is like this. So here this is the gate terminal, this is anode and this is cathode. If I draw again, it will, there is 2 arrow in anti-parallel like this, and here this is the gate and this is anode, cathode. So this is the symbol of gate turn off thyristor. Here also turn on and turn off can be controlled by gate terminal. So that's why this is also called a fully controlled switch. This MCT. So MCT also has 2 types, NMCT and PMCT. NMCT and PMCT. So its symbol is like this. So gate terminal is here, this is anode and this is cathode. So this is the NMCT type, and in case of that PMCT type, this is like, this is the gate terminal and this is cathode and this is anode. So this is the gate terminal. So here also that gate terminal is present. So by using this gate terminal, it can be turned on and turned off. So that's why this is also called a fully controlled switch. So these are the example and explanation of fully controlled switch. Let's move to the second classification of switches. So that is classification by charge carrier. Classification, that semiconductor switch can be classified by the based on their charge carriers, like a unipolar device or bipolar device. So that is unipolar device and bipolar device. And if it is a unipolar device, so that is the majority carrier device. And in case of a bipolar device, that can be majority carrier or it can be minority carrier device. Example of a unipolar device is MOSFET, JFET, Schottky diode, and these are the majority carrier device. And bipolar device are BJT, PN junction diode, thyristor family like SCR, TRIAC, GTO and IGBT. These all are minority carrier device and bipolar device. So that whatever that conduction is happening in these majority carrier devices, so that is because of one charge carrier. Because of one charge carrier. And here whatever that conduction is happening in case of that bipolar devices, so that is because of not because of that one charge carrier. So here electron plus holes are involved in the conduction process, but in case of that majority carrier device, electrons or holes, because of that any one of the charge carrier, conduction will be happen in case of a majority carrier device. So let's say understand one by one what is unipolar device and what is bipolar device, and see the explanation of all the devices like MOSFET, JFET and Schottky diode and all this. Okay, first talk about that MOSFET. So why it is called majority carrier device and a unipolar device? So in this, so it has 2 types. One is N channel, and another one is the P channel. So in case of a N channel MOSFET, so electrons is the majority carriers, only electrons is the majority carriers. And in case of a P channel MOSFET, holes are the majority carriers. So that's why, so in this, so since only one type of carriers participate in the conduction of MOSFET, like in the N channel only electrons are involved, in the P channel only holes are involved. So that's why this device is called unipolar device and majority carrier device. Now let's see the JFET. So in case of JFET is similar as MOSFET, so it has also 2 types. One is N channel, another one is P channel. So in case of a N channel, electrons is the majority carrier. electrons is the majority carriers, and in case of the p channels, holes are the majority carriers. So in these also only one type of charge carrier is responsible for the conduction process. So that's why this JFET is also called a unipolar device and majority carrier device. Okay, let's see that other devices. Schottky diode. So if we see the construction of a Schottky diode, so there is a metal semiconductor junction is there. So one is metal, so there is a metal semiconductor junction is there in case of a Schottky diode. So electrons in the n-type Schottky diode is mostly common. So current conduction occur only due to the one type of charge carriers. So here current conduction happen due to one type of charge carrier. In case of one type of charge carrier, so electrons in n-type and holes in p-type. So that's why here also only one type of charge carrier is involved. So that's why this Schottky diode is also called a majority carrier device and unipolar device. Let's see the bipolar device. Bipolar devices. The first one is BJT. So the BJT has two types. One is PNP, NPN, and PNP. So in case of that NPN, so that BJT has involved both type of charge carriers. Like in case of that NPN, electrons are majority carriers. Majority carriers in emitter, and holes are minority carriers in base. So this is for that NPN type. So in case of a PNP type, just opposite, that holes are the majority. Holes are the majority in emitter, and electrons are minority in base. So both the electrons and hole participate in conduction. So the device is called bipolar device. So that's why this device is called bipolar device. Okay, let's see the next device, that is PN junction diode. PN junction diode. So here also, like both type of charge carriers are involved in the conduction process. That electrons that majority in n region, and minority in p region. For the holes, majority carriers in p region, minority in n region. So in this for the conduction process, both the electrons and holes are participated. So that's why this device is also called a bipolar device and minority carrier device. When there is a PN junction, so that device is called minority carrier device. If any device create any PN junction for the conduction process, so that device is called minority carrier device. Let's see SCR. So in case of a SCR, so SCR is a 4-layer device, that is PN. So here also it's creating PN junction. So when any device create any PN junction, so that is a minority carrier device. Now in the conduction process, in the SCR also, in the conduction process, both electrons and holes are participated. So that's why SCR is also called a bipolar device. So next is TRIAC. So So TRIAC, so in the TRIAC also it's the combination of two SCRs. It's the combination of two SCRs. So as it is the combination of two SCRs connected in antiparallel in a single structure, so it can conduct current in both direction. But in the conduction process, both electrons and holes take part. So that's why this device is also called a bipolar device. Then GTO, gate turn off thyristor. So it has similar like SCR. So this is also a 4-layer device, and in the conduction process, both electron plus hole participated in the conduction process. So that's why this GTO also called a bipolar device like as SCR. Let's see that IGBT. So IGBT is the combination of MOSFET and BJT. So here whatever that conduction process, so that is done because of that BJT, that is based on that BJT characteristics. So IGBT is the combination of MOSFET and BJT. So the IGBT combines IGBT is the combination of that input structure of MOSFET with the conduction characteristics of BJT. So as a result, that both electrons and holes are involved. So IGBT is called a bipolar device. So this is also called a bipolar device. This is the explanation of unipolar device and bipolar device, and majority carrier device and minority carrier device. So let's move to the next classification, that is classification by power handling capability and switching frequency. So these are the devices, that SCR, GTO, IGCT, IGBT, power MOSFET. So power handling capacity of this SCR is very high, but its switching frequency is low, less than 1 kHz, and application in HBTC and rectifiers. Now if we talk about the GTO has very high power handling capability. The switching frequency is low to medium, less than 5 kHz. So its application in large drives and traction system. IGCT, the power handling capacity is high, but that switching frequency is medium up to 5 to 10 kHz. The high power inverter application of this IGCT, and IGBT, that is medium to high. So that up to 20 kHz, that motor drives renewable energy inverters. Then power MOSFET, low to medium, that is greater than 20 kHz up to megahertz. Its switching frequency is very high, and its application in SMPS DC to DC converters. So if we compare these devices, like SCR has very high power handling capacity but frequency is low. So similarly, see, if we compare this MOSFET and IGBT, so MOSFET has very high frequency, switching frequency, but power handling capability is less than that IGBT. But IGBT is the has very high power handling capability more than this MOSFET, but its switching frequency is less than MOSFET. So according to our application, we can choose the devices where we required high frequency requirement is required, high switching frequency is required. So at that time we will use power MOSFET. So where that power handling capability is more, so in that case we will select that IGBT. So based on that, we can categorize our switching devices according to that power handling capability and switching frequency. So this is the vast classification of switches or semiconductor switches and explanation. Thank you everyone.